Well, thank you for that introduction, and thank you for having me here. It's a great honor. I will tell you about both experiments. I'm heading the CMS experiment. This is a picture of CMS. It's a fisheye view. It's not really bent like that, or we'd be in trouble. And you can see the beam pipe going through it, and the detector opened up. And you're actually looking from the floor kind of upwards at the ceiling. So you see these are different stories. Anyway, I'll tell you about not only this experiment, but also the ATLAS experiment. The two experiments together were crucial in discovering this particle. We couldn't have done it with one alone. And I hope by the end of this you'll realize why, because it's quite difficult to find such a rare signal and to really understand it well. Okay, so see if this all works. I'm a bit jet lagged, so wake me up if I fall asleep. So I don't know the level of the audience, so I'm going to work at several levels. But hopefully, even if you have no background at all, you'll get something, and I'll keep you awake. I even have some jokes to keep us both awake. Okay, so anyway, so why do particle physics? Actually, particle physics is I think if I were someone out there, I would ask, why are you looking for these particles? There must be all kinds of particles. Actually, there are very, very few particles, and they answer very big questions. The really elementary particles are, you can almost count them on your hands and toes, and there are even fewer interactions among them. These particles, most of these particles that I'm talking about actually don't exist in the usual sense, and I'll get back to that. But they played a really big role in both determining how the universe is structured and evolved, and still how other particles interact and how other particles are structured too. So we still need to understand them, so we want to find and study them. And to do that, we have to basically recreate the period in our history, our universe's history, not our history, when they did exist in the usual sense. So this is the history of the universe in one slide. I'm not going to go through everything here in detail, but I think there's a pointer here somewhere. I have a lot of slides, so I have to go fast. But this shows the Big Bang. And sort of this vertical dimension tells you how big the universe was as a function of time. So it was small, and then it went through a rapid inflation period, okay? And this time axis here is very nonlinear. So here you're at 10 to the minus 44, 10 to the minus 37, 10 to the minus 10 seconds. Here you finally reach 2 minutes. And here you're at today, which is 13.7 billion years. So where do we work? We have two types of interactions we work with at the LHC. We actually collide heavy ions, lead ions together, and we work at about here, at about 1 microsecond, about 10 to the minus 6, 1 millionth of a second after the Big Bang. And then we also collide protons at higher energy, and we work around there, which is about 1 trillionth of a second after the Big Bang. So we're recreating what happened that far back. Somebody once asked me to describe what would happen next year, and I pointed out, I work in the past. I really have no idea. Now, what we've done over the last century or so in particle physics is we've gone to deeper and deeper levels and higher energies. And you probably all know this. Here's a block of matter. It's made up of atoms. The atoms have electrons surrounding a nucleus. The size of an atom is about 10 to the minus 10 meters. The nucleus is about 10 to the minus 14. And we now know that inside the nucleus, there are neutrons and protons, which are about 10 to the minus 15 and to 10 to the minus 18 for quarks. And that's as far as the structure goes that we know so far. But we're still probing. I'll come back to that in very briefly. And at the same time, we're going to higher and higher energies. And there's a correlation. Going to very high energy allows you to go to very small distance scales. So we work in electron volts. And I just want to give you a quick orientation to the units. 0.04 eV is what an atom is, the energy of an atom of air right here in this room. 1 to a few eV is what you get from chemical reactions, visible light. Millions of eV are what you get from nuclear reactions per atom, right? And the rest energy, don't forget, E equals mc squared. So the energy of a proton is about 1 billion electron volts. And that's a GeV, giga electron volts. So at the LHC now, we're colliding protons, and each proton has an energy of 4 trillion electron volts. So this is the highest energy ever reached. And we're able to probe to 10 to the minus 20 meters, so a factor of 100 below the size of quarks, very small. Unfathomable. I can't imagine what that means, really. Okay, and we work with something called the Standard Model, and you'll hear me refer to this, or you'll see SM referred to in the talk. So over the last 100 years, there's been advances in theoretical physics and the discovery of many, many subatomic particles that have allowed us to build something we call the Standard Model of particle physics. This is something like a new periodic table of the fundamental elements. But they're not atoms, they're particles. And this is what it looks like. It's rather simple. As I told you, there are very few fundamental particles that we know of. And this is one of the greatest achievements of 20th century science. And I'll tell you more about it. Now, the matter particles, the particles that we think are the type of particles that can build structure, are called fermions. And the particles that carry the forces are called bosons. Okay, so I'm not sure if you know this. I'll very quickly tell you about it.
What you just said, the difference?
The particles that make up structure, matter, are fermions. And the particles that make up force fields are called bosons. There's an error in this page. I'll see if anyone gets it. A mathematical error. Enrico?
Isn't it Sachin for not?
It's Sachin for not. Yes, I couldn't fit. N is for not.
Oh,
Yes, yes. No. It's actually Enrico Fermi has the. This formula is wrong. This is a famous. It's a famous photo. It should be E squared over H bar C. Eek. You've got to remember. Anyway, probably he didn't do that. It was a photographer. I know what that's like. So bosons are named after an Indian physicist named Satyendranath Bose, and fermions are named after Enrico Fermi. And there's a big difference between these particles. First of all, bosons have integer spin values. Spin is intrinsic angular momentum. And photons, this is Bose wrote to Einstein and told him that he concluded that photons tend to clump together in the same state as a result of a deep quantum mechanical effect. And in fact, all fields, we know all fields have energy quanta associated with them, and the field quanta for all forces are bosons. These are the force carriers, as I just said. Now, fermions are named after Fermi. They have half integer spin, and they can't be in the same state. Identical fermions can't be in the same state. Electrons cannot be in the same state, and that's how you build atoms. They just keep filling different states, and you build shells. So they build structure, okay? That's the difference. Okay, now back to the Standard Model. This is a picture showing all the particles I showed you before, but on a mass scale. And you can see there's a big difference in the masses. The electron actually is much lighter than the top quark. In fact, it takes 344,000 electrons to make up a top quark. We don't exactly know why the top quark is so heavy, but it is very heavy. These, the up-down quark and the electron, are all you need for everything we see. The up and down quark make neutrons and protons, which make nuclei. Add electrons, you have atoms, and you have everything, pretty much everything you see. But we found that there were actually 3 generations of these kind of particles, okay? And there's this one missing piece, which is the Higgs. And that was missing for a very long time. But we think we have it. Why do we need it? Well, the force carriers mostly are massless. But the W and Z force carriers, they carry the weak nuclear force. They had to be heavy. We knew that was true because we knew that this force was short range. And that's by definition meaning that whatever is carrying the force is heavy. So if you put masses in by hand, everything seems to work until you go to high energy. And at high energy, the model breaks down. In fact, what happens is that some processes, in fact, some types of particle scattering suddenly goes to have probabilities greater than 100%, which is not possible. That's called unitarity violation. You're violating the maximum probability, which is 1. So, and there's the gauge symmetry is violated. Now, gauge symmetry, if you know electricity and magnetism, you know that there's a gauge symmetry to electricity and magnetism, just classically. Gauge symmetry is very important in particle physics because it was discovered that when you introduce the gauge concept, to quantum mechanics and then to quantum field theory, it tells you how the particles interact with the fields. It tells you perfectly. So the hope was that we could describe all forces as gauge fields, but this one broke that. But the key was to find a loophole, and the loophole, the potential way out of this problem was to assume that maybe the universe is just different than we thought. The rules are okay, but the playing field is different. And to this extent, the idea was that we would fill the universe with some sort of a field. And this turned out to give stability to the standard model at high energy, provided that the field that we added was made up of bosons with no spin at all, which we've never seen, by the way. We've never seen spinless particles that were fundamental. This field turns out then to interact with the W's and the Z particles, as I mentioned. It kind of impedes them. It stops them from being able to move at the speed of light, which is effectively saying that they have mass. So it makes them massive. The underlying theory remains a gauge theory, as desired, okay? But its true nature is hidden by the fact that the universe is permeated by this field of constant strength. And in fact, this field, we say in physics, has a non-zero expectation value everywhere, meaning that all the universe somehow is filled with a charged medium. But it's charged not electrically, it's charged in the weak sector. Have I lost you all? Or are you okay? Okay. So this is just a picture of the idea. You have a uniform field. I've shown it as a grid, but it's uniform field. And some particles attach to this field, or the field attaches to them. It shields their energy, concentrates it, and you create a massive particle. Okay. Now there are fundamental connections between fundamental particles that are, this is kind of interesting, and it's an interesting aspect of quantum field theory. They really are interconnected, all these fundamental particles. And that's why we study them, as I said earlier. So for instance, the mass of the W particle depends a lot on the mass of the top quark. Here I show what's called a Feynman diagram of a W transforming into a top and a bottom quark, and then back into a W. This is a virtual process, okay, that we have to take into account in order to get the calculation of the W mass correct. It can also depend on the Higgs a little bit. Here I show you a process where the W radiates the Higgs and reabsorbs it, a virtual process. These things have to be taken into account to get the mass of the Higgs correct, mass of the W correct. And the conclusion, therefore, is that the identity of a particle is not really separable from what it can become or what it can decay into. You can't really do that in quantum field theory. So the upshot is that if you were to measure the top quark and the W mass very precisely, you could predict the mass of the Higgs in the standard model. And in fact, as of summer of 2011, this is where we stood. This took a very long time because these are rare particles and they're difficult to measure. So after 20 years almost, how many years? 16 years of study, we got the top quark mass to almost 0.5% precision. And after 30 years of study, we had the W mass down to parts in 10,000. And if you put those together and take into account that we'd already ruled out a mass of the Higgs up to 114 from direct searches, then there was a 95% chance it would lie between 114 and 185 GeV. Don't forget, a GeV is about the proton mass. But we couldn't be sure until we looked, so we really had to look. And it could have been somewhere else. The standard model might be wrong, for example. All right, so I'm going to kind of conclude this little section on the theory. So how can you think of all this? Well, you could think of space-time itself as being something of a fabric that has interesting properties. It really is not empty in the purely empty sense. It is something that encodes all the particles that can exist and how they can interact with each other. And there are virtual particles that can interact with real particles. I showed this, where the W can virtually transform into other particles and back. And particles can interact with the Higgs field, virtual particles from the field. And in fact, if we can concentrate enough energy in one small region, we can pull new particles out of this fabric. And we can make heavy particles that we have not seen before. And that's what we try to do. Because they'll tell us something about the underlying code of the universe, which is fairly simple, but we need to understand it correctly. So how do we get so much energy in one spot? We use a Large Hadron Collider. Hadron, by the way, just is a generic term for any particle that's made up of quarks. Okay? And this is a picture, my favorite picture of the accelerator complex. My house is just over, no, I'm just kidding. But this shows you how big this accelerator is. There is a series of accelerators, actually, that are required We inject from one to the next, increasing the energy each time. And you can see the Alps. This is a nice clear day. And here's the injector chain. So we start with a linear accelerator, either with the heavy ions, as I told you, but let's stick with protons. That's what we use for the Higgs. You accelerate them to a certain energy, and then you put them into a little booster, and it accelerates them to a higher energy, goes to another ring, to a higher energy, and finally into the LHC. And the reason for this is that the particles are easy to accelerate because they're charged, they're protons. You can accelerate them in an electric field. But as you accelerate them, you want to keep them, you don't want to lose them. So we keep them on a circular track. So each time we give them a little kick in energy as they go around the circle, and then we have to raise the strength of the magnets to hold them on that circle. It's kind of like having a racetrack where you can control the banking, okay? But at a certain point, you run out of control. It depends on the size of the track, right? And how far you can push the banks. At that point, we transfer to another bigger accelerator and do it again, and just go to higher and higher energy. So you get about a factor of 10 to 20 in energy for each step. Now, this is the inside the tunnel. The biggest challenge was building these 15-meter long dipole magnets. We had to build 1,200 of them. The ring itself is 27 kilometers. These magnets can go up to 8 Tesla. It's a very strong magnetic field. And that allows you to hold up to a 7 TeV beam. Remember, TeV is trillion electron volts. So in fact, there's a simple formula. The momentum of particles that you can handle in TeV is 0.3 times the field strength in Tesla times the radius in kilometer of your circle. Everything's linear. If you can build a bigger accelerator, you can go to higher energy with a fixed set of magnets. With a fixed tunnel, you have to go to higher strength magnets. So these dipoles have 7,600 kilometers of niobium tin titanium superconducting cable, 12 kiloamp current maximum, operate at 1.9 degrees Kelvin using 120 tons of superfluid helium. So it's quite a big system. In fact, it's the largest cryogenic system on the planet. The vacuum inside the beam pipe is better than on the moon, and it's colder than deep space. And a lot of that technology to do that is being used for other things that I won't have time to go into that. Practical things, unlike this. But it's like, I like to say, it's like Swiss chocolate. You'll have to think about that for a minute. The magnets have a huge store of energy. In fact, it's enough to melt 12 tons of copper. That's the energy in the magnets. And that's the kinetic energy of an A380 at 700 kilometers per hour. How much energy is stored in the beams? It's actually equivalent to 90 kilograms of TNT or 15 kilograms of chocolate. All right, so let me tell you about the experiments, and I'll start with the competition, but let me show you all of them first. So here's the ring. Here's another picture of the ring and the various chains. This is the main laboratory. To get a scale, here's Geneva Airport, and you can see the Lake of Geneva and so forth. There are two really big experiments, ATLAS and CMS, and these are what we call multi-purpose experiments. They try to do everything, okay? And then we have a couple of somewhat smaller experiments called LHCb and ALICE. LHCb focuses on B quark mesons. Mesons are hadrons with only 2 quarks. And they study those to try to understand why there's more matter in the universe than antimatter. And ALICE studies heavy ion collisions only. But the two big experiments, ATLAS and CMS, do everything. So we compete with each other and with the other ones, and we look for everything. So here's ATLAS. This is a drawing. What they wanted to do was build a system with very large toroidal magnets. This is a sketch from many years ago showing this is where the magnets would be. They'd be kind of like this, going in and out of the plane. You see the fields, and the idea is the particles go through those would be bent. The trajectories would be bent, and the curvature would give you the momentum of those particles. And that's for the muons. So that's a very long time ago. And this is the actual toroids being built. And you start to get a sense of how big these detectors have to be. And this is the actual detector with the toroids in place before the central detector is in place. And this is a person for scale. So these are enormous superconducting toroids to create magnetic fields for deflecting muons. This is the cavern in June 2003. The experiments and the accelerator are all about 25 stories underground. And this shows the installation of these giant toroids. I don't have a nice animated set like that for CMS. but I'll show you a bunch of separate pictures. So this is Atlas, a schematic diagram of the whole thing. The length is 46 meters, about 150 feet. It's 24 meters in diameter, so that's about 75 feet. And it weighs 7,000 tons, has 3,000 kilometers of cables. Here's people, just give you a sense of how big it is. I think those are small people, though. The size, in France, they like to use French people who are on average a little bit shorter. It makes the detector look like, no, I'm just joking. The size and the mass of this detector is really is what is required to measure the momentum of very high energy particles, because you're trying to curve their trajectories and measure that curvature, right, to determine their momentum. If they're very, very high energy, they may deflect very little. So you may need a long distance over which to deflect them. And that's why these detectors are so large. They use a relatively strong magnetic field in the central part of the detector, but it's not as strong as CMS. And CMS is then built to be more compact as a result. I'll show you that. But there's about 100 million independent sensing channels, if you like, individual signals that come out. We can track 1,000 particles per event. We reconstruct all of their trajectories with a few micron precision, which is pretty impressive. And these things have to be built to very high radiation tolerance. It took us many years to learn how to do that. We had to develop new technologies to do that. They can handle up to 10 to the 17th neutrons per square centimeter, which is 10 to the 7th gray over 10 years. And Atlas is made up of a big collaboration, 38 countries, 175 institutes, 3,000 authors, of which about 900 are students, graduate students. CMS is here. I won't go into great detail on this drawing. I'll show you lots of pictures, but you can see it breaks apart into many modular pieces. The central, most important piece is a 3.8 Tesla solenoid. Because we have such a strong magnetic field, we can build it to be much smaller radius and shorter. And in fact, it's 1/4 the volume of Atlas. But it's twice the weight. In fact, considering it's only about 75 feet long and about 50 feet tall, it's surprising that it weighs twice as much as the Eiffel Tower, I think. And that's because there's so much iron. All this orange that you see is iron that has to soak in that very strong magnetic field so it doesn't just leak out everywhere and destroy all of our equipment. So CMS had to be built on the surface and lowered 30 stories in big pieces, about 13 big pieces weighing about 1 million pounds each. And so this was a big headache for us. We had to build it in a modular form, but it turned out to be a big benefit now because we can open this up and get access to it very easily. And I see that the newer or future experiments all have a design that's similar to this now. For us, it was just a necessity at the time. This is the biggest piece being lowered. It has the magnet. We had to rent the largest crane in Europe to do it. And the magnet is about 35, 40 feet long and has a diameter of about 20 feet. So it's a huge magnet. Here you can see it. You can really stand a lot of people inside it. As I said, it's 4 Tesla, has 20 kiloamps current. Stored energy is almost 3 gigajoules. So it's got to be extremely strong. It's the largest, most powerful superconducting solenoid ever built, in fact. One thing we did was we recycled some turning weapons into plowshares. Is that the same? So these are old artillery shells from the Russian Northern Fleet, World War II. And we melted them down. Here's a cheerful guy. And we turned these into our energy measuring devices, our hadronic calorimetry. And this is just showing you how complicated the cabling is. It took us 50,000 man-hours to actually install all the cables. And this shows you the last piece being installed. And again, I show you some people to set the scale. And then it's ready for close. And CMS, like Atlas, has about the same number of scientists, engineers, technicians. We have 42 countries, about 1,500 PhDs and 800 PhD students from 190 institutes. And one of the nice things about these experiments is that we work so internationally. And if I had the time, I would show you how almost every piece you look at came from a different country, all came together, all fit. We have countries that are in principle hostile to each other, working together very harmoniously, and it's a very nice aspect of what we do. Part 2, how does it all work? Well, we have the beam is not continuous. There are 2 beams, 2 beam pipes. They're going opposite directions. They cross in the middle of our detector. each beam is made up of about 1,400 bunches. Each bunch has 150 million protons in it. And so when they pass through each other, because protons are so small, even though it's 150 billion in each beam, and even though they're focused down to about 1/10 the diameter of a human hair, we only get about 20 or 30 pairs of protons that collide. Now, I'll tell you a few things about this business. Because we're colliding protons, protons are made up of quarks and gluons. It's kind of like throwing bags of particles at each other. The protons aren't solid. What collides is what's inside them. And we call these quarks and gluons inside partons. And each parton carries a fraction between 0 and 1 of the proton's momentum. So I'll give you an example of a d-anti-d interaction in a proton-antiproton collision, which we don't do at the LHC, but it's the only drawing I had at the moment. And you see, basically, the d will collide with the anti-d, and something will happen. But the d is carrying some fraction x1 of the proton's momentum, and the d bar is carrying some fraction x2. So the center of mass energy of the actual collision that we're looking at is different from the proton center of mass energy. And we can't predict what it is from event to event. We can predict what it'll be over many collisions. So there's, let me skip that. So there's a couple of implications. One is that we don't know what the boost will be of the entire event frame, because one of the quarks coming in could be more energetic than the other. But we do know that there's no momentum perpendicular to the beam initially, so there can't be any imbalance afterwards, conservation of momentum. Because of that, we work with transverse variables. So the transverse momentum is conserved, and so we'll often talk about transverse momentum, transverse energy, and things like this. We also use, instead of, partly because of this random boost that occurs, we use, instead of cylindrical coordinates, we use something I like to call relativistic cylindrical coordinates, where instead of theta, we use eta, which is pseudo-rapidity, and it's the log tangent of theta over 2, and it has a very nonlinear scale, but it turns out to be very, very useful in describing particles under these circumstances. Anyway, this is a picture of CMS before we closed it with the end caps. I'll show you how the detector works in this frame. You see lots of cylinders, right? So basically, that's how it works. We use different cylinders, nested cylinders, to do different things. This is just a schematic. Now I'll get rid of the detector, and I can show you what happens. So we start in the inner region with very, very lightweight semiconductor layers, for example. Many, many layers, super lightweight. If a charged particle passes through them, it leaves a little bit of charge, and we can locate that charge to a few microns, which is a 10,000th of an inch. And what happens is we get many of those layers, and we connect the dots. And we see that we can reconstruct the tracks, and we can measure their curvature, and from that get their momentum and so forth. Then what we do, so that's all happening in here. Neutral particles don't leave any tracks. Then just outside that, we put very, very heavy detectors. And those heavy detectors stop the particles and make them shed all their energy. And a lot of that energy appears as light. We measure the light, and from the light, we can calibrate and get a measurement of the energy. So we have two types of detectors. One is for electromagnetic particles, electrons and photons, and one is for hadronic particles, ones with quarks. So then you see, in our case in CMS, then we have the solenoid, the magnet, and then outside that, the only thing that can get through all of that material, there's 14,000 tons basically, are neutrinos, which we don't see at all. We can't stop them, we can't detect them. So we infer their existence by an imbalance in the transverse energy, if momentum is not conserved. And the other thing are muons, which I have somewhere here, a muon. A muon will come out and actually change direction. So that's how it works. This is an actual collision. That's a very interesting collision because there are 4 muons. See, these 4 particles got through many layers and all the way out to the outside. So basically, the way these detectors work, you can think of them as ultra-fast digital cameras. They have about 100 million pixels, and they can take 40 million pictures per second. So they have a fast response of about 25 billionths of a second. All channels, all 100 million channels have to be synchronized to about a billionth of a second, which takes some time. Particle trajectories are reconstructed, as I said, with a few microns of precision by 76 million channels of silicon detectors in the case of CMS. And interesting collisions are very rare. We only record about 500 events per second out of the 16 or 20 million per second that occur. So we have to pick the good ones, and we pick them fast. And we still end up with a lot of data, in fact, and we transport it all over the planet. We have about 22 petabytes collected at CERN in 2011 and 30 petabytes in 2012. A petabyte is a million terabytes. No, wait. A petabyte is a million gigabytes. So it's a lot of data. And this grid that we use has about 250,000 computers in 50 countries. But we can actually get the data distributed very fast now, and we can do analysis very quickly. So how well does it all perform? This is the accelerator. The efficiency of the accelerator was only 16% in 2010, and by 2012 it was 37%. It's a very complex machine, and in fact, historically, 20% is outstanding. So it's really been a fantastic machine compared to previous accelerators. And the detectors have worked outstandingly well. So this shows all of the subsystems in Atlas, all working at 95 to 100%, and the same for CMS. Everything's above 95%. And in fact, this means the data quality is very high, and all of our results are based on about 90% of all the beam crossings, which is pretty astounding for new detectors of this complexity. Okay, this shows the intensity of the beams over time, and they just kept going up and up and up, setting records. But in 2012, we stabilized at 7.7 10 to the 33 hertz per centimeter squared. That's probably completely irrelevant to you, but it's a very high rate of collisions. And one thing that was happening that I'll talk about more is that we had more and more proton pairs colliding, okay? We call that pileup. So in 2011, the average number was between 5 and 10, and it went up to around 20 to 25 pairs of protons. So what does that mean? For us, experimentally, it's a big headache, and I'll show you why. If you look, I'll come back to it in a minute. But in 2010, one thing we did that was interesting was this is the history of particle physics, all the major discoveries, all of which I think won, or most of them won Nobel Prizes, from the muon all the way up to the top quark in 1995. It took about 70 years. And we were able to redo the whole thing basically in 1 year at the startup of the LHC, which was pretty spectacular. Okay, so I mentioned this pileup. This shows you what we're dealing with. So this is a real event, and I've color-coded individual proton-proton interactions, and you see there are many of them, and all of these particles are going out into the detector, but only one of these interactions is interesting. We have to then weed it out from all of this background. So this is looking, if you like, at the side. So the beam's coming from the two sides of the detector, you understand? And you're looking at the detector from the side. If you were to look at it from the beam's point of view, this is what it would look like in 2010 when we had typically 2 pairs of protons colliding, in 2011 when we had 5 to 10, and this is 2012. So this shows you what we're dealing with. This is all background, if you like. This is all noise we have to pull out. Remarkably, the young experimentalists in the collaborations found ways to do this very quickly and very impressively. So I'll tell you some of the things we do. One thing is we look for very interesting particles, namely electrons, muons, taus, photons, and we typically ask that they're isolated. The reason is that they're usually coming from an interesting particle that should just decay on its own, like a W or Z or something like this, or a Higgs, for example. You could have a quark or a gluon that's very energetic coming out, and it tends to form many, many particles in what we call a jet. If you find one of these interesting particles inside a jet, there's a good chance it's a fake. In other words, it's not really a photon. It's probably a pi0 to decayed to 2 photons or something like this. So to avoid these kind of faking, we ask that there's no activity around the particle we're interested in within a cone that surrounds it. Now what happens though, as you have more and more of these collisions, you find that this is the number of collisions going from 0 to 40, you have more and more jets, okay? So there's more things to kind of crowd the system. And that means, in fact, that if you're looking for photons and you're requiring them to be isolated, your efficiency drops. And this is a key channel, 2 photons for the Higgs. And you see we're losing a lot of signal when we're asking that the energy around the candidate photon in the calorimeter be very low in a cone around it. So it's very hard to be isolated. But if you can track the particles back to where they came from, you could figure out whether they came from the same vertex or not as the things you're interested in. And in fact, when we look at tracking, we found that the efficiency stayed very flat. So both experiments learned how to do this. The tracking systems are really phenomenal. Here you see an event I show from CMS. Here's a very low momentum particle, and you see it just gets caught in the magnetic field and loops many times. And this can all be tracked and recorded digitally. Here you see a jet. There are many particles coming at high energy in this direction. Yeah. Oh, that's a good question. It's still moving. It depends what it is, but it's probably moving at a pretty high velocity still, close to the speed of light. And so if it's at the speed of light, this radius might be of order meter, 2 pi r, 6 meters. So you're talking about maybe 20 meters. Speed of light is 3 nanoseconds per meter, so about 60 nanoseconds. Okay, yes?
I don't think I understand what you mean by a jet.
Well, a jet this is not the greatest picture because you don't see the tracks, but a jet, as I said, I didn't want to go into this in great detail, but I will do it. Not in great detail, but it's a very interesting aspect of quantum chromodynamics, of the strong interaction. If you take a quark at very high energy and try to give it a kick, it has the funny property that it always has to stay associated with another quark. And what often, you can think of it almost as having 2 quarks on the end of a string. If you try to pull the string apart, you introduce enough energy that it splits, and now you have 2 strings with 2 quarks, and this keeps happening. So if you take a very high energy quark or a gluon, which will then split into quarks as well, and you try to kick it out on its own, instead of going out on its own, it produces a shower of particles all in roughly the same direction, and we call that a jet. Okay, and jets are very, very common. I'll show you that in a second. All right, so we took taking control of pileup, as I said. Here you can see zeta mu mu in Atlas, 98% efficiency, independent of how many vertices there were, electrons in CMS. And really importantly, measuring the missing energy. Missing energy is really important to look for things like dark matter and so forth. And you can see that the resolution, the uncertainty on the missing energy measurement was rising rapidly with the number of pileup interactions. But once we took into account tracking, we flattened it out. And the same is true in CMS. Here you can see it extending, that's to 18, all the way out to 35, still remains fairly low. Okay, so I think I'm almost through the more technical part of the talk. So how precise can we be? So I want to just show you 1 or 2 slides on standard model studies that we use in some sense to calibrate our ability to do good work. So here you see a really beautiful spectrum of photons or Z's decaying to pairs of muons in the CMS experiment. The black dots with the bars are data, and the blue line is the prediction, and you can see that this is over almost 10 orders of magnitude. And I've never seen anything like that in my career. And this is the ratio, certainly at this early point of an experiment. You can see it's basically matching to within a few percent. And Atlas shows here the probability of producing, I thought this is top, says W plus jets. So W is plus jets, and the probability of producing additional jets from gluons or quarks. And you see very good match to theory. This is a much more rare process than this. And in fact, if we look at many different processes, the cross-section basically gives you the rate at which they occur. And I'll show you how, these are already all very rare processes. The data are the little circles with the little bars, vertical bars, and the lines, the horizontal lines actually show you the theoretical predictions. And so over time, we were able to study more and more rare processes all the way down to pairs of Z's. Atlas doing the same, very good control. And so we had a very good understanding, very good theoretical predictions too. I want to say that the theoretical community was able to do very hard calculations that had not been done before for us to be able to check these things. Excellent control of the backgrounds, and so we're basically ready to hunt for the Higgs. And this is where we stood in July last year. Now quickly, this is again talking about the theorists. There's kind of a revolution that's going on in calculating to higher and higher orders in perturbation theory. So this is calculating more and more terms in a series that allow you to get very precise predictions of strong physics, quantum chromodynamic processes, which are very hard to calculate. It used to take 10 years to get to the next order. Now it's just a couple of years, but they're still incredibly difficult. So this, again, is where we're studying. I've showed you, this is the range of rates that we're looking at, these processes I showed you. If you go over here, this shows you the total rate. So this is the rate at which collisions are happening in the LHC here. The processes that we're looking at over there are between here and here. So we start at already 6 orders of magnitude below the total rate, and go all the way down to about 11 orders of magnitude below. And this is where we'd predict the Higgs to be, in this range down here, depending on its mass. Okay. The Higgs is produced many different ways. The dominant way is through gluons, which are massless. Remember, the Higgs couples to particles with mass, so this seems a bit strange. But actually, the way they get around that is the gluons will fuse, will produce top quarks that fuse. Tops are extremely heavy. They like to talk to the Higgs. So you get a little triangle here of top quarks, and that generates a Higgs. You can have vector boson fusion. Vector bosons are the W's and Z's. Here you have them fusing to form a Higgs. You can have a vector boson, a W or a Z, radiating a Higgs, or you can have a Higgs radiated from top quarks when they're produced. And these are all lower and lower rates. Now, all of them are very, very low rates. So to increase our sensitivity, we actually look at all of these channels, one way or another. Now, in the end, that's just how they're produced. How does the Higgs decay? In the mass range we're interested in, which is this gray band, there are many different channels that we can look. And in fact, we look at all of them, all of the ones shown here, some of which are very rare. For instance, 2 photons is relatively rare. And here you see Z's to 4 leptons is much rarer, okay? But it turns out to be very useful anyway, even though it's very rare, because it's very, very clean. So the most sensitive ones are the Z's, then the photons, then the W's, then the taus, and the B's. And these two are the ones I'm going to concentrate on because they're easiest to understand, and they're the most powerful because they form very nice resonant peaks. So for instance, if we look for 2 photons, this is simulated data where the signal is at 130 GeV. And what you see is that from standard processes, we expect a background that's falling very steeply that's huge. But the signal should be very narrow and should appear as a little bump. This is a very old plot going back 10 or 15 years, I think. So we expect about 500 Higgs events to be reconstructed, and that will be sitting on a background of 18,000. So it's tough, assuming we find them. And depending on what mode you look in, you can get higher and higher purity, but very largely reduced numbers of events. A crucial issue then is the resolution of the mass. The peak has to be very narrow if we're going to see it. Otherwise, it's just going to be washed out. The other channel is the Higgs to 2 Z's, where the Z's both decay to electrons or muons, and then you get an incredibly beautiful peak. This is for 145 GeV, which is high, and it's for a lot more data than we had. But you can see the signal compared to the background is very clean. So this is a very clean channel, even though it's very rare. And the signal background is about 1 to 1, which is fantastic. It's actually better than that. We have to go very low in the energy of the electrons and muons, really low. 5 GeV is quite low for us. And the crucial thing is the reconstruction efficiency. How well can we find these electrons and muons and put this all together? Because you're looking for 4. Now, the 2 experiments use different technologies. In CMS, we use lead tungstate crystals to look for photons, for example. So we have 76,000 of these crystals. They look just like glass, but they weigh more than gold. And they give us incredible resolution on energy, 2 to 5% over the square root of E. So here you see what we'd expect for the Higgs, about a 1% resolution. Atlas uses a liquid argon calorimeter, sampling calorimeter, which has 10% over root E. It's a little bit worse resolution, but it has more granularity, more segments, and it allows them to actually track photons in their directions, which we can't do in Atlas, and that's a benefit for them. It's very important to have 2 experiments with different technologies. One technology may fail. We like to have different systematics. We want to be able to compare different approaches. All right, so I'm moving on to the discovery. This is a Higgs to 2 photon candidate event. This is a real event. You see lots of debris from breaking up protons rather, but in the central region, moving perpendicular to the beam, there's 2 huge photons that are matched back to back and very high energy. And there's no track pointing at them. That's why there's a dashed line. We know they're photons because there's no charge track. And this reconstructs to about 125 GeV mass for if you assume that it came from a single particle. So if we do this with many, many events, remember I told you you'd see a very steeply falling background and a small bump. And this is what we saw. Very small bump. So you can ask, what's in this bump? Well, it's a few hundred extra events with 2 photons that reconstruct to 125 GeV. And you ask how many collisions did it take to find these few hundred events? It actually took 10 to the 15th. So 1,000 trillion proton-proton collisions. And this is why I was saying it's so difficult to do what we do and be sure we've got it right. But what helped a lot was Atlas presented this. And it's, that's a nice coincidence if it's a coincidence. So then you look in other channels. This is a Higgs to ZZ candidate event where both Z's, one is red, one is blue, decay to electron-positron pairs. And when they collect all of their 4 lepton events that reconstructed this way, they found an excess of events at about 125. And CMS also saw that. So both experiments saw these small bumps, these very rare processes at exactly the same place at the same time, and we really never talked to each other. So it was very exciting. We presented this in a big seminar at CERN. It was simulcast to a big meeting of our field in Melbourne. What surprised me was that we've never had so much press attention before. There's some interesting ones here. I like this one. How will it impact financial services? I don't know. But it turned out that over 1 billion people saw television footage of this thing, and there were 17,000 articles written in 108 countries. So somehow it captured the imagination of the world, which we did not expect, frankly, and it's been great. It's very rare that basic science is popular. so we'll take it when we can get it. Last part of the experiment, of the talk rather, is determining, is it really a Higgs or not? At the time of the presentations on July 4th, we said it was Higgs-like. It resembled the Higgs, but we didn't know if it was a Higgs. So I like to say, is it Higgs-like or a Higgs we like? So it's a very interesting question, and I'll tell you how we determine that we think it really is a Higgs. It's a very special particle that has a very important relationship to the weak force carriers and the electromagnetic force carrier. In fact, it's part of the unification of those into one field theory. And here are the equations, which I won't make you suffer through too much, but it's called, what's involved in creating the Higgs field is called the Brout-Engler-Higgs mechanism of electroweak symmetry breaking. And in the process of this mechanism, the W and Z get massive, as I told you before. The photon remains massless by introducing this scalar field. Scalar field means a field made up of bosons, the particles with no spin. This field that we introduced, this Higgs field, has a potential associated with it, and there's 2 constants that are important, mu squared and lambda. And what happens is at some point during the evolution of the universe, the sign of mu square flipped from positive to negative, went from a positive value to a negative value. And when that happened, the mu squared, this quantity flipped sign, mu squared flipped sign, so you had a potential that was like a nice deep well with a central symmetric point for the lowest energy point. This is what you always like to see, right? And it transformed into what we call a Mexican hat, a sombrero, and the universe rolled down this hill and chose a point somewhere on the base, okay? Now the symmetry is broken, okay? It's not in a symmetric point, it's at some random point on the circle, but it's broken spontaneously. We don't know how it chose it. Actually, if you want a good analogy, it's like molten iron. If you take molten iron, there's no orientation of the magnetic, of the little, of the spins and of the magnetic fields of the iron. It's all random, so it's all zero, if you like. It's all perfectly symmetric. As it cools through the Curie temperature, they start aligning, and they form domains in which the magnetic field is aligned, right, in iron. Do you know about this? That's also spontaneous symmetry breaking, and in fact, it involves the same potential, only it's classical in that case. Anyway, the reason I mention all this is from this, we know that there's a vacuum expectation value. There's a value to this field. It's no longer at zero. It has some value. And we can calculate the Higgs mass. It has this quantity in it, which we don't know, lambda. But we can calculate everything else. And we can find the W and the Z mass, which we calculate. And we can predict that the electron mass and other fermions also acquire their mass the same way. And the couplings, this is the strength at which they couple to the Higgs, should be proportional to their mass. That's the key thing to remember. If it's a Higgs, it should be spin zero, and the connection it has to other particles should be proportional to their mass. If you don't remember anything else I told you from this slide, just remember that. So if it's a Higgs, those are the two questions you want to answer. Is it spin zero, actually in positive parity, meaning it can't have any substructure, it's just a fundamental particle, and does it have coupling to other particles that are proportional to the mass? And if that's true, then there are many other questions you can ask. Is it really elementary? Is it composite? Does it have some negative parity? Do its couplings, even though they're close to the standard model, do they deviate from expectations? Could it decay to invisible particles? Is there new physics involved? Those are questions that we're working on already, but we'll spend the next 20 years trying to answer. I'll talk to you now about the top two. First, I want to mention that we continue to look. We have 3 or 4 times as much data as we had in July. The signal's still there in the photons. In CMS, it actually got a little bit weaker, interestingly. It got closer to the expectation from the standard model. The ZZ channel got much bigger. It's very, very, very clear now. And taking all this together, we can look at the couplings to various particles, to vector bosons, to fermions, to the WZ, to the quarks, leptons, and so forth. And this chart tells you that if everything were like you'd expect in the standard model, you'd line up along that dashed line. And within the uncertainties, it seems to do that. Same thing in Atlas, but you can see it more clearly if I plot it as a function of the mass, okay? And that's here. So the strength, the apparent couplings that we see really seem to be proportional to the mass. What about the spin? Well, it's hard to see it, but what you do is you look at the angular distribution of the decay products. And so I won't go into detail here, but we look at various channels, we look at the angular distributions, we compare what we'd expect for, say, 0 with negative parity or 0 with positive parity. Those are the dashed versus the solid line, and you see the data matches much more closely to the positive parity. And in fact, we rule out the possibility that it's spin 2 by 99.9%. We ruled out that it's 0 minus by 99.8%. We ruled out that it was spin 1 by 99.9%. So the indications are that it's spin 0 plus. So it seems to be a Higgs. So in March, we went out and actually told people we thought it was a Higgs. And that surprisingly also became a big event news-wise, and I'll come back to that in a minute. This is just the signal strengths. Everything is consistent. If it were the standard model, this should be 1. So within sort of 1.5 sigma, we're matching the expectation of the standard model. But we have to remember this is still early, and we want to get a lot more data and understand this a lot better. But as I was saying, we put out a little tiny press release saying that the new results indicate that this new particle is a Higgs boson. That was a big week, by the way. Do you remember they were picking a pope, actually? And then I saw this, Higgs boson, a new pope. So anyway, you never know what to expect from the press. Now, one interesting thing I want to finish now, because I know I'm close to using up my time. I want to tell you something interesting, which is the mass of this particle. We can measure the mass from the peaks. Where's the center of the peak, basically? And so Atlas looked at their photons and Z's. They get 2 different values that average out to 125.5. CMS gets 2 different values that are a little bit closer. They average out to 125.7. So it really seemed to be very close. But this mass is a very interesting mass. It turns out, remember I told you there's this potential that is a Mexican hat potential, and that the universe now is ridden down to the base of some point in this potential. Well, it turns out if you know the Higgs mass very well, and you know the top quark mass very well, you can predict the shape of this potential. And in fact, there are regions of the masses where the potential doesn't exist. It's flat. The universe would be unstable, it would break down. That's these red regions. There's regions where it's very stable, meaning that the potential is very deep. The universe is stuck deep in there. It's not going to come out. And there are cases where it's shallow, and quantum mechanically we know that things can tunnel out of shallow potentials. And that's a metastable region. Well, wouldn't you bet it that we're living in a metastable region? So it turns out that the universe is not entirely stable, and it's not unstable. And we think it has a lifetime of about 100 billion years. So it's not worth worrying about at the moment, anyway. But one thing we want to do is actually get these measurements much more precise, and the calculations as well. You should take all of this with a grain of salt, because there's a huge amount of calculational work that has to go behind this, and the measurements we'll do of these two quantities, the top quark mass will get about a factor of 3 or 4 more precise in the next 20 years, and the Higgs mass will get about a factor of 10 more precise. And so we'll find out where we stand. This is also, I should say, in the standard model. I don't know exactly what would happen if the standard model were not the final story. There's one other thing I want to tell you, so you know what we're doing next, and then I'm done. There's a problem with the Higgs mass. If you do a calculation of a particle, remember I showed you before that the W mass, we had to add these additional terms for other particles that it could transform into. You can do the same thing with the Higgs, and for all the standard model fermions, you add this loop correction. But because the Higgs is spin 0, it turns out the calculation diverges. And the mass actually goes to be a really huge value. Basically, we think it would go all the way to the Planck mass, 10 to the 19th GeV. And we measured at 125, so we're only off by 17 orders of magnitude. You know? It's almost like astronomy. Excuse me. I'm joking. But this is something that's called the hierarchy problem. And there are a couple of ways to get around it. Yeah, 10 to the 19th. It should be 10 to the 19th GeV. It's much bigger, much bigger. So it could be, if you calculate it, I'm sorry, that's the calculational value. It's wrong by that amount, yes. So this is either a theoretical or a philosophical problem for us, because either there's something theoretically missing that cancels this out, or philosophically, there's the possibility that the universe is just perfectly tuned so that all the cancellations work and this works. And it's called the fine-tuning problem. But we've never seen a natural system that was that finely tuned. So there's a way around it. The solution would be to add new particles that would cancel those effects, okay? And you need partners to all the standard model particles, particularly to the top quark, which contributes the most. And the question then is, how do you get these partners to the standard model? One way, it's kind of the typical way, is using what's called supersymmetry. This is a very basic symmetry. It completes the Poincare group, for example, of symmetries. And it basically says it transforms, it's a transformation from any fermion to a boson, or from any boson to a fermion. So for every fermion in the standard model, there's a boson partner, according to this, or for every boson, there's a fermion partner. Now, there's some really interesting effects when you include supersymmetry into the mix and add that to what we know about the standard model. For one thing, if we go back in time, the strengths of the different forces vary as you go back in time to higher and higher energies, but they don't converge. If you use supersymmetry, they actually converge to a point, which many people find compelling as possible, not really a coincidence, something that's really of interest. It also, in supersymmetry, in the simplest models of supersymmetry, predicts that we should find a Higgs that's very much like the standard model Higgs that's less than 130. And as I just showed you, we found something that's 125.6. And the third thing is, it provides some clues to the dark side of the universe, which is dark matter. And so last I'll mention is about this. There's a cosmological connection, which is dark matter. Starting with Zwicky and other astronomers, it was noticed that stars are moving a little bit too fast as you move away from the center of galaxies or clusters. And Vera Rubin cataloged many, many galaxies, and what they did was look at basically Doppler shifts and measure the velocities as a function of radius from the center. You expect that the velocity would tail off like this. This is the prediction, and this is what's observed. It's actually rising. So it's as if the stars are embedded in something that's pulling them around. And this is called dark matter. A Swiss physicist by the name of Zwicky coined the name in the 30s, and we have much better evidence now that it's there, in fact. So what the heck is it? So to understand it, we have to go over to the dark side. And we now know, in fact, that about 5% of the universe is ordinary matter. About 28% is dark matter. These are recent results from the Planck Observatory. And supersymmetry has dark matter candidates, okay? And in fact, you find that it predicts about this amount for what we should have now in the universe. The puzzling thing is we don't find it at the LHC, but we're looking. The remainder of all the energy in the universe is dark energy. We're not sure what this is really. We have, it'll probably be TAC someday. There'll be a Department of Dark Energy perhaps, but we've looked. We've done actually hundreds of searches for dark matter or anything related to supersymmetry. In fact, we have over 550 publications from the 2 experiments in the first 3 years of operation. All of them are breaking new ground in one way or another. Many of them are searches for SUSY and new physics, but we don't see anything yet. The Higgs discovery papers, by the way, already have almost 2,000 citations, so there's a lot of interest in those. So we have this interesting situation that we found the Higgs, and as Guido said, it's very simple, like the standard model Higgs, but very unnatural, meaning we don't find anything else to explain how its mass could be there in a natural way. It showed up exactly where no one expected it to be. This is where you'd expect it if it were supersymmetric. This is where you'd like to see it if it were a standard model. Sort of fell in between, and that's a big clue. So we're going to go to 65% higher energy in 2015, and we hope to find some evidence of supersymmetry that would really, or something that could explain how the Higgs mass is stabilized at low values. So what next? It's exploration. We don't know what we'll find, and well, we'll just have to see. So let me wrap up. So it was 48 years since the idea of the Higgs mechanism was hatched. It took 20 years to design and build the experiments. It was 3 years to acquire the data. It was actually a generation of work by thousands of people. And all they got for this was this stinking T-shirt. Actually, no, there was also, it was really hailed as a major discovery, and I think it's very important, and we'll have to see where it takes us. It certainly was nice that it won a Nobel Prize. So Francois Englert and Peter Higgs, remember I said the mechanism was the Brout-Englert-Higgs mechanism, but Brout died in 2011. And Higgs, the Nobel cannot go to someone posthumously. So Francois Englert and Peter Higgs won, and it was no coincidence that it was because of what we saw. So we were very happy when it was announced, as you can see. So that's all. Thank you.